Yeah. Good morning, all the students. Yesterday I forgot to orient you on this quizzes event. I'll do that today at the end of the class. Anyway, I have put a reminder for that also. Before that, I'll share my presentation to finish today's class. For your first internal, you'll have first chapter completely and second chapter, 1/4 of the second chapter. Okay, that I'll complete in tomorrow's class. Now let's move on to this 8th lecture under module 1. This is the last concept we are going to deal with in this particular module. Before going to that last concept, let's see what we have done in the previous classes. We have understood what is a version space and how this version space is used by the candidate how this version space is given as output by the candidate elimination algorithm, right? So a version space is defined as set of all the hypotheses H that are consistent with the training examples D, right? This is called as the version space. This version space will have two sets, the general set and the general boundary set and the specific boundary set, right? So these two sets will shrink as much as possible as and when the version space learns better and tries to get a more general concept to predict any new data point, right? That is called as the version space. The candidate elimination algorithm starts with all possible hypotheses and tries to eliminate every hypothesis whenever it is found not to be consistent with the training example. Finally, it gives us output a version space, which is the set of all hypotheses that is consistent with the training examples D, right? So that we have seen even the steps involved in candidate elimination algorithm, and we have understood that candidate elimination algorithm with an example also. Yes, students, you want to speak? Okay, now let's learn about what is inductive bias. What is bias? Can anybody give an example of what is bias? If I teach only some highly developed concept so that only fast learners in the class will understand and slow learners can't keep track of that. In that case, I am said to be biased towards fast learners, right? And if I take the population count in the world and I do that count only in the eastern part of the world, not in the western part, then I say my study is biased only to the eastern part of the world, like that. Say if I'm trying to understand about some gender specific concerns or issues faced by the students, and I mostly interview only girl students and very less number of boy students, then I say my survey or study is biased towards girl students, right? So if I'm not taking a representative sample in order to make my study, that is called as a biased sample. Or bias means there is some deviation, there is some limitation in the study I make. Okay, so now what is inductive bias? We have understood what is inductive learning, right? Inductive learning is based on the examples given, you try to learn some rules out of it. That is called as inductive bias. Then inductive learning. Then what is deductive learning? You are given the rules and you will be asked to apply those rules practically and understand the concept. That is called as deductive learning, right? Because these two terms we are going to use in today's class. First, I want to make you clear about all these separate terms. Okay, so bias is some say partiality kind of thing that I have in my study. Okay, and in inductive learning, we study from the observations or examples, and we try to find out some rules. Okay, we try to formulate some rules. But in deductive learning, rules are given, say, to the students, and they're asked to learn from those rules the underlying concepts. That is called as deductive learning. Means you're deducing some concept from the rules given to you. But when you are inferring some rules based on the example observations given, or when you are learning some concept, when you're learning some inference rules kind of thing, when you are given the observations or examples, in that case, it is called as inductive learning, right? So you clearly now notice the difference between inductive learning and deductive learning. Now these terms we are going to use in this concept, inductive bias. Any doubt in this? Inductive and deductive learning? This is called as inductive learning. This is called as deductive learning, right? If you are trying to infer rules from observations, it is inductive learning. If you are trying to learn a concept from existing rules, then it is deductive learning. Okay. Let's move forward. The candidate elimination algorithm will converge towards the true target concept. When it will converge towards a target concept, when it will make the version space lesser and lesser with fewer number of hypotheses that are consistent with the training examples, when it is given accurate training examples. Training examples should be accurate. They should not contain any noise. Means there should not be any outliers or missing data or duplicate data in the training examples. In that case, the candidate elimination algorithm will surely converge to a version space which has all the hypotheses that is in compliance, means in accordance with the target concept that has to be learned. Now, one more, its initial hypothesis space contains the target concept. Remember, the initial hypothesis space that is being used by the candidate elimination algorithm should contain the target concept. Only then it will be able to converge to a point where it contains all the hypotheses that are consistent with the training examples, that apply to all the training examples. Now, what are the fundamental questions for performing this inductive inference? In order to perform this inductive learning, what are the fundamental questions that we come across? What if the target concept is not contained in the hypothesis space? Okay, if the target concept is contained in the hypothesis space, it can learn and eliminate some hypotheses which are not applicable, and finally come out with a set of hypotheses that are consistent with the training examples. Okay, because the target hypothesis or the target concept is already existing in the hypothesis space. If at all the target concept is not covered in the hypothesis space initially, what will happen? Let's see. Can we avoid this difficulty by using a hypothesis space that includes every possible hypothesis? Now, if for every training example, if you want to include all possible combinations, can we avoid the above difficulty? Yes, let's see. How does the size of this hypothesis space influence the ability of the algorithm to generalize to unobserved instances? Now, you have more and more number of hypotheses. Does it guarantee us that it will generalize to unobserved instances? Means it will generalize to unseen data? Means whether it will classify correctly the unseen data? Let us read again. How does the size of this hypothesis space influence the ability of the algorithm to generalize to unobserved instances? If more and more hypotheses are available in the hypothesis space, does it guarantee that our unseen data can be correctly classified by the learner? How does the size of the hypothesis space influence the number of training examples that must be observed? Now, you have all possible combinations of the attributes in the hypothesis space H. Now, in order to eliminate those hypotheses which are not applicable, how many training examples have to be given to the learner? If less number of training examples are given, more hypotheses will be present because the learner can't learn from less number of training examples. So it can't eliminate what hypothesis that doesn't apply. Okay, its learning, its knowledge is very less. When the knowledge is very less, how can it eliminate the hypotheses that are not applicable or consistent with the training examples? So what should be the size of the training examples that should be given to the learner in order to reduce the size of the hypothesis space? Okay, these are various questions that will be encountered, and let us see whether this inductive bias concept or inductive learning concept will help us to answer these questions. Now, a biased hypothesis space. What is a biased hypothesis space? I'll tell you, it is quite easy. The terms are actually somewhat scary, but the concept underlying is very easy. Only thing is you have to focus, that's all. A hypothesis, a biased hypothesis space. When do we say that a hypothesis space is biased? Means it is not covering sufficiently all the training examples. Say when I perform a study about only girls and very less number of boys, my hypothesis space is biased towards girls because I considered large number of them and very less number of boys. I can't generalize properly, right? Okay. Now suppose we wish to assure that the hypothesis space contains only known target concepts. In textbook, it is given in different way. I think you will not understand that line. So replace that line with this. I made it somewhat easier. Okay. And for this particular concept, all of you can go through the slides and take the notes. This will be enough, whatever I have given in the slides. Do not refer the textbook for this particular concept because it is too lengthy, and for you to cover it will take more time. Those students who want to learn deeply have to surely refer to the textbook, but if at all there is a time constraint in order to learn before the exams, you can take help of this slides for this particular concept, right? I have made it more brief and easy for you to understand and further present it in the exam. Now, a biased hypothesis space we are trying to understand, right? Suppose we wish to assure that the hypothesis space contains only known target concept. It should not contain any unknown target concepts. Okay, means it should cover all the training examples, and there should be no hypothesis which doesn't cover any of the training examples. That is our objective. Now, the obvious solution is to enrich the hypothesis space to include every possible hypothesis. So what is our motive now? In order to start with, in order to see that hypothesis space doesn't miss out any of the target concept, we will include all the concepts, all the hypotheses that are applicable. Okay, all the hypotheses that are relevant. Now consider again the enjoy sport example, same example we'll take throughout this chapter, in which we restricted the hypothesis space to include only conjunctions of attribute values. What do we mean by this? Listen carefully. Now, when we have taken the hypothesis space for enjoy sport, what we have done? We have taken the conjunctions, means for this particular training example, 1, when it is sunny and warm and normal, I am using and is a conjunction, and normal and strong and cool and change. Only then it is the predicted as S. Okay, so what is the constraint we have imposed in our hypothesis space? What is the restriction we have put on the hypothesis space? It should contain only conjunctions of the attribute values. Means only if all this combination, only if this entire combination is true, then predict it as S. Got it? If any of this is not true, it doesn't cover that situation at all. The hypothesis space is unable to represent even simple disjunctive target concepts such as if the sky is sunny or Disjunction is given by this symbol. Conjunction is given by this symbol, right? Now, say if the target concept is sky equal to sunny or sky equal to cloudy, what will happen? Either this is allowed or this is allowed. In that case, our hypothesis space doesn't have such kind of hypothesis. Now, given these three training examples, let us take these three training examples of this disjunctive hypothesis. Our algorithm would find that there are zero hypotheses in the version space. Isn't it surprising now? Actually, when the learner starts learning from example 1, it has some specific hypothesis. From example 2, it generalizes this sky attribute and still has some specific hypothesis, right? But when we take this disjunctive representation of the target concept, means instead of and, if we are using or, we'll find that there are zero hypotheses in the version space. Why? Because, listen carefully, up to this training example, what can be our specific hypothesis? Question mark, warm. After observing the two training examples, this will be our hypothesis. Question mark, warm, normal, strong, cool, and change. Right? This will be our specific hypothesis as the learner observes the first two training examples. Now, the learner encounters this third training example. It doesn't know, assume that it doesn't know about the prediction. What would it predict? Can anybody tell me? Only rainy is changed. Observe this. Warm, normal, strong, cool, and change all are same. Only rainy is changed. But already that is represented by a question mark. Now what does the learner predict it as? Yes or no? Are you there, students? Give me the answer. With what label it predicts this third example? Based on the hypothesis, specific hypothesis that is learned till till two training examples.
Yes.
It will give us S. Why? Because first any value is allowed, right? Because it is a question mark in the hypothesis. Rest all values are same. That is why the learner will predict it as S label, but actually it is a no label. Means whenever this hypothesis is found to be inconsistent with the training example, immediately it will be removed from the version space. Do you remember? Whenever a hypothesis is found to be inconsistent with the training examples, candidate elimination algorithm will remove that hypothesis from the version space. So this hypothesis will be removed from the version space, though it covers example 1 and example 2. That is why there will be zero hypothesis in the version space. Repeat this video if you didn't understand. I have explained very clearly. Okay, so because of this last training example, which is not covered by the hypothesis that is learned so far, that hypothesis will be removed from the hypothesis space, resulting in zero hypothesis in the version space. Okay, that is why we call it as biased hypothesis space. It is covering some training examples and not covering some training examples. So we call it as a biased hypothesis space. Right? Now note that that is what I explained you. The most specific hypothesis consistent with the first two examples and representable in the given hypothesis space, H is this one, what I have written there. Now, although this is the maximally specific hypothesis, from H that is consistent with the first two examples, which is already overly general, it incorrectly classifies the third training example. That is why it is removed from the version space. right? So the problem is that we have biased the learner. Understand this concept, it is very important. The problem is we have biased the learner, means we have told the learner, that is the machine, learn only for and combination of the attributes, conjunctive combination of the attributes. Do not learn anything about disjunctive combination of the attributes, right? We are saying the learner only when all these together are true, then predict it as S, or only when together are true, together of these attribute combinations are true, then predict it as no. But we are not giving it any other alternative than this. That is why we call our learner as a biased learner and our hypothesis space as a biased hypothesis space. Got it? Now, what is an unbiased learner? Okay, we understood that our learner is biased. Now, how to make it unbiased? Let's see. The obvious solution to the problem of assuring that the target concept is in the hypothesis space H is to provide a hypothesis space capable of representing every teachable concept, every possible concept, every possible combination. Okay, say if I have two attributes and two values allowed for those two attributes. So the power set will be what? 2 power 2, right? Say I have A and B as the values. Now I can write it as AA, AB, BA, BB. Okay, you know the power set, right? In mathematics, power set is all possible combinations of the elements. Okay, if there are two elements, then the power set will be 2 power 2. Now, let's come back to our example. In the enjoy sport learning task, for example, the size of the instance space X of days described by, of days described by the 6 available attributes is 96. Means, let's say sunny attribute will allow 3 values and humidity attribute will allow 2 values. Say forecast attribute will allow 2 values. Like that, you have some allowed values under those 6 attributes. Now, what are the possible combinations? 3 into 2 into 2 into 2 into 2 into 2. So 96. From that, how many instances can you generate? Power set of that. That is 2 power 96. The amount is very huge, right? Thus, there are 2 power 96 or approximately distinct target concepts that could be defined over this instance space and that our learner might be called upon to learn. If at all you want to start with all possible hypotheses, if this is the example training set given, in that case, 2 power 96 hypotheses have to be included into the hypothesis space to start with. And whenever a hypothesis is found to be inconsistent with the training example, that will be removed. Again, when it is inconsistent with another training example, another hypothesis will be removed, right? And finally, a version space will be obtained, which will have only the hypotheses that are consistent with the training examples. Got it now? So we are trying to start with all possible hypothesis in order to make a learner unbiased. I'm not supporting this cause that a learner should be unbiased. I'm telling if a learner is unbiased, let us see what will be the problems. And we have to go back to biased inductive learner only. We have to make the learner biased. Unbiased learner will not help us. Why? Because can any learner learn from these many combinations? And if at all those many combinations have to be applied to a new training example, is it a valid scenario? No. So you have to make the machine smart enough to work with less amount of hypothesis, right? That is why let us see what kind of problems we encounter with this unbiased learner and how we go back to our biased learner only. Now let us reformulate the enjoy sport learning task in an unbiased way. Let us see. Let us start with an unbiased way only. Let us find all the possible hypotheses into the hypothesis space. Let's see what problems we encounter and which will drive us towards going towards biased learner. Okay. Now let us reformulate the enjoy sport learning task in an unbiased way by defining a new hypothesis space H dash that can represent every subset of instances. Means every possible combination of instances, let us put that into this hypothesis space H dash. Now one way to define such an hypothesis space H dash is to allow arbitrary disjunctions, conjunctions and negations of our earlier hypothesis. Means now how would the instances be? Sunny and it can be followed by any value. Cloudy, it can be followed by any value. Rainy, it can be followed by any value. In the same way, for wind, it can be preceded by any value. Wind should be strong. It can be succeeded by any value. When I am saying any, it can be or. When I say it should be all, then it will be a end symbol. Okay. So I am telling now any value can be allowed with this combination. Any value can be allowed with this combination. Any value can be allowed with a different combination. Means I am trying to include each and every possible combination of the attributes into the hypothesis space H dash, so that I will not make a mistake of not including the target concept into the hypothesis space. Okay, my initial assumption, I made it comfortable so that I include all possible hypotheses. Right, I started with all possible hypotheses. Now, though this eliminates any problem with expressibility because you're trying to express each and every combination possible, this eliminates the problem of expressibility. But what is the other problems that will arise? What are the underlying problems that will arise when you're starting with a hypothesis space that contains each and every possible combination of 6 of these attributes? What are the other problems that may arise? It raises a problem that our concept learning algorithm is now completely unable to generalize beyond the absurd examples. Remember, this sentence is very important. Now, you are giving to the learner any possible combination is correct. Now, when a new instance is given, means when a new data point is given where it has to be classified as no, what is happening? For any type of combination, you are asking the learner to predict it as yes, but actually its outcome is no. So what is your learner doing here is it is predicting everything as yes now because you have all the possible hypotheses. That is not correct, right? Let's see how it is happening. Suppose we present 3 positive examples, x1, x2 and x3, and 2 negative examples, x4 and x5. Positive examples means an instance whose label is S, an instance whose label is S. x3 is an instance whose label is S, and x4 and x5 instances label is no. The training example is no. Now, the S boundary of the version space will contain the hypothesis in which is just the disjunction of positive examples, right? Now, you remember the candidate elimination algorithm. Whenever an S label is encountered, you come from the top to make the specific boundary set more specific. And whenever a negative example is encountered, you come from the bottom. That is, you come from a general boundary set to make it more general. or make it, more specific. From topwards, if you're coming down, a specific hypothesis is being made more general. When you're coming from the bottom, a general hypothesis is being more specific, right? In that case, the S boundary of the version space will contain the hypothesis, which is just the disjunction of the positive examples, right? So whenever a positive example is encountered, how will the version space be taken and the specific boundary set be taken now? It will take it as x1, or it can be true for x2 also, or it can be true for x3 also. That will be the specific boundary version space now. And how will the general boundary change? Similarly, the G boundary set will consist of the hypothesis that rules out only the observed negative examples. Means it will say not x4 or x5. For all negative sets, it is again taking the disjunction. Before we used to take the conjunction. Now, because we want to make our learner unbiased, we are taking the disjunctions also. Now, whenever a negative example is encountered by the general boundary set, what it will do? It will say that it doesn't apply to that disjunction of those negative examples. No, it is a no. This hypothesis is a no for these two, for disjunction of these two instances. Now the problem here is, what problem we are encountering because of this representation? The problem here is that with this very expressive hypothesis representation, it is highly expressive. It is trying to cover any alternative. The S boundary will always be simply the disjunction of the observed positive examples, while the G boundary will always be the negated disjunction of the observed negative examples. Got it? That is what we represented. Now, the only examples that will be unambiguously classified by S and G are the observed training examples themselves. But if a new data point is given, it may succeed to predict or it may fail to predict correctly. I'm repeating again, the only examples that will be unambiguously classified by S and G here are the observed training examples themselves, right? It has all possible hypothesis means it will say S to all possible training examples. And in order to converge to a single final target concept, is it possible? All these hypotheses are applying to all the training examples. That is why you haven't removed any of this hypothesis from the hypothesis space. Means you're not able to shrink the version space. In that case, this hypothesis space will always make a true prediction only. It will not make a false prediction at all. Now, if a new instance whose outcome label should be no, still it will predict as S. Means it is misclassifying. It is not able to generalize properly. That is what is expressed in the last line, last point. In order to converge to a single final target concept, we will have to present every single instance in X as a training example, right? And that target concept is having lots of hypotheses. What is the use if it is not able to generalize? Let's proceed and see. The futility of bias-free learning. The what we say, futility means the harshness or the unbelievable facts, or what better word we can use here? Something like the drawback. Okay, the harshness it is showing on the search space by giving lots of hypotheses which can be dealt with in the real time. Okay, the futility of bias-free learning. Now, the fundamental property of any inductive inference is what? A learner that makes no a priori assumptions regarding the identity of the target concept has no rational basis for classifying any unseen instances. Okay, what it is telling is, if it doesn't make any assumptions, what is the assumption made by candidate elimination algorithm? All the disjunctions of the hypothesis should be considered. All the conjunctions of the hypothesis should be considered. Disjunctions should not be considered. That is the basic assumption made by the candidate elimination algorithm. Like that, any learner, though it is seemed to be biased, it have to depend on some assumptions in order to make the learner generalizable. Understood clearly? Though you say that a learner is biased, it has to start with some a priori assumptions. A priori means before starting the algorithm, candidate elimination algorithm, what assumption it is making? That all conjunction of the attributes only should be considered for the hypothesis. Disjunction should not be considered. Okay, such kind of assumptions are very much required for for an inductive learning in order to make that learner generalizable, in order to make that learner predict most of the new points correctly. Remember, I'm saying most of the few new points. All points it can't predict correctly, but most of the new points it has to predict correctly. Means it should be highly generalizable. In order to make it highly generalizable, we have to make some a priori assumptions. And what is the a priori assumption made here by the candidate elimination algorithm? That it has to consider only conjunction of the attributes, values of the attributes. Means only all the combinations together should be true. Any of the combinations, if it is true, it doesn't consider, right? So candidate elimination algorithm is able to generalize beyond the observed training examples in Enjoy Sport task, as it was biased by the implicit assumption. It is biased by the implicit assumption that the target concept could be represented by a conjunction of attribute values. So it has a bias initially, it has an assumption initially. What is that assumption? That all the target concept should be represented only by conjunction of the attribute values. Disjunctions are not allowed, right? That is the assumption made by this Enjoy Sport task learner. Only, and that is why it is able to predict correctly most of the new data points. That is what it is saying. If it is correct, its classification of new instances will be correct. But if the assumption is wrong, only small number of instances may be predicted as negative labels or positive labels wrongly, right? It may make wrong predictions if its assumption is wrong, but that will be less number. It will not be more, like in case of unbiased learner, right? So what is the basic idea of inductive bias? The key idea we wish to capture here is the policy by which the learner generalizes beyond the observed training examples. What is the idea or what is how a learner will generalize beyond the training examples to new data points? What is the assumption it has made? By considering that it is conjunction of the attributes to infer the classification of new instance. That idea is used to infer the classification of new instance. So the key idea we wish to capture here is the policy by which the learner generalizes beyond the observed training data to infer the classification of new instances. The policy here is make assumptions. The policy used by this particular idea is make assumptions. Assumptions have to be made. Though some predictions are wrong, still assumptions have to be made. Now consider the general setting in which the arbitrary learning algorithm L is provided an arbitrary set of training data DC, which contains the set of attributes and the target label of some arbitrary concept C. Right. Now after training, L is asked to classify a new instance Xi. See, it will be a little interesting here. After training, L is asked to classify a new instance Xi. Learner now knows everything what is applicable or consistent with these training examples DC. Now it is asked to predict what is the outcome of this Xi. Now let L Xi DC denote the classification, that is the outcome yes or no, that L assigns to Xi, to which class it is assigned yes or no, after learning from the training data DC. Now we can describe this inductive inference step performed by L as follows. How do you describe that? DC and Xi can be represented like this. What is this symbol here? Not greater than, it is something like this. This symbol is called as inductively inferred from. If I say Y, this symbol Z, then I can read it as Z is inductively inferred from Y. Okay, Z is inductively inferred from Y. Now this symbol we can read it as inductively inferred from, but we have to read it from the other side, right hand side. Z is inductively inferred from Y. Okay, let's see why we are saying that in this case. This new label is inductively inferred from the training examples and applying that to the new instance. Okay, for that, let us take the new instance of the day's climate for various attributes. Okay, we have taken A, B, C, D as the new instances where the outcome label has to be predicted. Now, the inductive inference performed in this case concludes that what it concludes? This new instance is predicted as S. How is it predicted as S? Because you have a specific hypothesis in the hypothesis space, right? Which is true with a positive example. In that case, this is also predicted as S. Now, what additional assumptions could be added to this training example and this new instance so that this will follow deductively? Means by making some assumptions, we are able to perform some inductive learning. By taking some assumptions and training examples, we are able to predict something, right? We are able to infer something. Now, is the other way correct? Means, can we say that all these assumptions made are okay for this particular inductive learning? Let's see. Now we define inductive bias of L to be the set of assumptions we make B such that for all new instances, it should contain the set of assumptions, it should contain all the training examples, and it should contain the new instance also. Now when all these come together, then you can deduct the new prediction of Xi. This symbol is called as follows deductively. Okay, follows deductively from. See, say this is followed deductively from this. Right hand side is followed deductively from this. Left hand side means you're trying to predict something. You're trying to predict L of XIDC, means you're trying to predict the new instance by making some assumptions by learning from the training examples so that it can generalize well on the training instance, new instance. Okay, that is what we mean by this deductive learning. Okay, when we are learning it one way, we are checking whether it is correct the other. We are making some assumptions and the learner is making some assumptions and it is learning. Now it is once again checking back whether the assumptions are correct or not. That is why this inductive and deductive learning are working here together. Thus, we define the inductive bias of a learner as the set of additional assumptions B sufficient to justify its inductive inferences as deductive inferences. Got it? Now we are justifying all its inductive inferences, whether they can be justified as deductive inferences, all these assumptions made, whether they are okay with this outcome that is predicted. If this prediction is correct because of these assumptions, we can say that using these assumptions is correct decision. But if the prediction is wrong, we can't immediately say that this assumption is wrong, but we'll try with some more new instances. If repeatedly it is giving wrong prediction, then our assumption may be wrong. But only for some instances it is giving wrong prediction. But most of the instances it is giving correct predictions. In that case, we say our assumptions are correct. This is called as deductive learning. From assumptions, some predictions are made. Now these predictions are validated against these assumptions. If these assumptions are, if these predictions are suitable with these assumptions, means if predictions are correct with these assumptions, then we can justify the usage of those assumptions. Okay. Now this is the last slide. Bear with me. I think we are ahead of, yeah. These are the formal definitions for inductive and inductive bias and this one, inductive learning. Okay, consider a concept learning algorithm L from the set of instances X. Okay, now we are understanding about a concept learning algorithm L for the set of instances X given. Now let's C be the arbitrary concept defined over X, and let the training examples be defined as X and C of X. We know this representation. Be an arbitrary set of training examples of C. That is the target concept. Now let the learner predict a new instance Xi by learning from the training examples DC. Let this denote the classification assigned. Now this new instance, by learning from these training examples, it is predicted as S or it is predicted as no, right? Denote the classification. Let this denote the classification S or no assigned to the instance Xi by the learner after training on the data DC. That is how we read that. L of Xi, DC means how do we read it? This denotes the classification assigned to instance Xi by the learner L by learning from the training examples DC. Got it? Now the inductive bias of L, how do we define the inductive bias? Say, whenever a survey is made in any of the research, there will be an inductive bias. There will be some assumptions. Okay. Now the inductive bias of L is any minimal set of assumptions. Assertions they have given, it is assumptions. Okay. Any minimal set of assumptions B such that for any target concept C if you take and corresponding training examples DC, how do you define that? For every new instance that belongs to X, the classification of that new instance can be deducted from combination of the assumptions, the training examples, and the new instances attribute combinations. Got it? I'm reading this once again. For the inductive bias of L is any minimal set of assumptions B such that for any target concept C and corresponding training examples DC, how it is defined mathematically, for every new instance that belongs to the instance set X, you can predict the label of that new instance. You can deduct the label of that new instance. This is deduct. Okay. You can deduct the label of that new instance with the help of assumptions made and learning from the training examples. You means I'm telling about machine. Okay. Machine will make use of the assumptions, training examples, and the new instances attribute combinations. All these will be used to predict the label of this new instance. Okay, so the inductive bias of candidate elimination algorithm can now be defined as the target concept C that is contained in the given hypothesis space H. Now it is simple. The inductive bias of candidate elimination algorithm is just explained in one sentence. After understanding all this throughout the session, in one single line, the inductive bias of candidate elimination algorithm is explained. What it is? The target concept C is contained in the given hypothesis space H. That is ensured by the candidate elimination algorithm by assuming an inductive bias. by making some assumptions, right? So it is assuming that only conjunctive combination of the attributes should be available in the hypothesis space, and it also assumes that it covers the target concept. That is the assumption for inductive bias. See, that is clearly explained with these two diagrams, simple diagrams. Okay, training examples and new instances are provided to the inductive system, which will classify a new instance as yes or no. But in deductive system, what will happen? Along with training examples, along with new instance, B is also provided. That is the assumption that H contains the target concept. This assumption is very much important in order to reduce the hypothesis space and make the learner more generalizable to predict more labels correctly. Okay, so this assumption is added to the deductive system, which will again give a classification of a new data point, whether it is yes or no. In inductive systems, only training examples and new instances are taken. In that case, we call it as unbiased learner. But when assumptions are also joined with that, then we call them as biased inductive learning, or we can also call it as deductive system, right? Because we are checking the other way, whether our assumptions are correct or not. Right, so what are the advantages of this inductive bias perspective? It provides a non-procedural means of characterizing their policy for generalizing beyond the observed data. Okay, this inductive bias perspective will characterize, one second. Yeah, this inductive bias perspective is like a non-procedural means. It doesn't follow any procedure, but it helps us to characterize the policy for generalizing beyond the observed data, right? That is called as inductive bias perspective. Now it allows comparison of different learners according to the strength of the inductive bias they employ. So we will be able to compare what type of inductive bias it is employing in these algorithms. There is a learner called as rote learner. In this rote learner, what it does is, see, it will store all the training examples in the memory. Now, when a new training example is given, if that training example is as per the learned training examples, it will classify. Otherwise, it will reject that new instance. It will not classify it. Okay, that is done by rote learner. Means it is not having any inductive bias. It is simply rejecting this type of example I haven't seen, so I don't want to classify that. Okay, that is the decision made by rote learner. Now in candidate elimination algorithm, what it does? It takes help of all the hypotheses to agree on the classification of a particular training new instance. Okay, that is done in candidate elimination algorithm. But in finders algorithm, it will take the most specific hypothesis that will apply to all the training examples. Okay, that is how we can compare different learners by using this idea of inductive bias, right? So this is how we complete our first module. In next class, we'll start with the second module until whatever concept we complete in the next class, till there you'll have it for the first internal exam. And let me tell you in 2 minutes what is this quizzes event. I'll share my screen on that event day with you, and that will display one code for you to join the website and the code for you to join. You can join from your phone or from your laptops, and whenever all of you join and the number shows that all students have joined, I'll immediately make the quiz live. Okay, when the quiz started being live, then immediately you have to start answering, and you will have a leaderboard where based on the number of correct answers given by the students, your name will appear at the top of the leaderboard. And also, if multiple students have answered the same questions, same number of questions correctly, in that case, in minimum time they answered, that will be considered. So how quickly you answer the quiz also matters here. Based on the time you have taken to answer the quiz questions, based on that you will top the leaderboard. Okay, so this will be a fun event. You will be seeing live who is on the top of the leaderboard, and if you quickly answer further questions, though they will also come to the top of that leaderboard. Okay, this event I am going to conduct tomorrow at 2 o'clock. Okay, not 2, 2:40, because tomorrow afternoon you have a class. After that class, 2:40 to 3:10, you'll have this event, and let's see who will win this quiz, right? Okay, any doubts so far, students? All of you marked your attendance? Only 33 students today? Okay then, meet you in the next class with second module.